Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over bond order and how to calculate bond order using molecular orbital theory. So in this problem I'm going to go over three examples, and we're going to see how the difference in the number of valence electrons in your molecule can either add to or take away from the stability of the bonding. And so the first thing you want to be able to do is you want to be able to draw your molecular orbital diagram. And so the way you draw your molecular orbital diagram is you have the atomic orbitals on the sides, and the atoms of those orbitals are here. So you can see that we have hydrogen here and hydrogen here, and you have your H2 molecule in the middle. So this is your molecule. So your molecular orbitals are in the middle. And so these orbitals are determined, or are created or come about by the linear combination of the atomic orbitals. So it's like the averaging, weighted averages of these atomic orbitals, kind of like sp hybridization, or your hybridization in the valence bond theory. And so you have your atoms here, you have your orbitals, so you have your 1s orbital here. So these are the atomic orbitals. And so these atomic orbitals are either going to interact constructively or destructively. So if they interact constructively, they're going to end up on the bottom, lower energy. So this is going to be your sigma. It's going to be a sigma, and it's 1s. The sigma 1s, because it's the 1s orbitals that are interacting. And then you can interact destructively, which is going to be higher energy, less stable. So this is going to be your sigma star, and that's again the 1s, your sigma star 1s molecular orbital. And so remember, the idea is the number of orbitals you put in, the number of orbitals you get out. They're the same. So the number of orbitals you put in is the same as the number of orbitals you put out. Okay, so again, that's the same thing with valence bond theory. So if you put in an S and 3 P's, that's 4 atomic orbitals, so you got out 4 equal energy sp3 hybridized orbitals, right? So you put in 4, you get out 4. You put in 2, you get out 2. Okay, so the next part is merely once you've got your orbital diagram set up, then the rest is easy, because all you're going to do is you're going to take the valence electrons, the total number of valence electrons from each of your atoms, and then fill in the orbital diagram. And you're going to use it using the same principles as before. The Aufbau principle, where you build up, you start low energy and you work your way up to higher energy. And in addition, you use the Pauli exclusion principle. So only 2 electrons in an atom, or in an orbital, no more than 2, and they both have to be opposite spin. And then also the Hund's rule. So Hund's rule says that if you've got 2 orbitals of equal energy, then you fill in 1 orbital at a time with 1 electron, both spins the same, spin up, and then you start pairing them up. So all the rules and principles apply to the molecular orbital diagram. Okay, let's get into this. So each hydrogen has 1 electron. So if you put in 1 electron, right? So now, if we've got hydrogen, here we have H2. So when you bring them together, so our molecular orbitals, we have 2 electrons. So we're going to fill in from the bottom up. Here's our first orbital that gets a maximum of 2 electrons. And we're going to put it spin up, spin down. Let's make this one spin down. It doesn't matter. So these 2 electrons come together, spin up, spin down, they're paired. That's all we have. So this is the molecular orbital diagram for for H2. And so we can figure out the bond order by adding the number of sigma bonds or bonding or molecular orbitals, and subtract from that the number of anti-bonding electrons, the electrons that are anti-bonding orbitals, and then you divide by 2. So here, for H2, the bond order is going to be equal to, we have 2 electrons in a bonding orbital. We don't have any in the anti-bonding orbital. We're going to divide by 2 and we get 1. So the bond order for this is 1, meaning it has a single bond. So it looks like this. So one single bond there. So we have a single bond, which is normal. Now, what if what about H2 minus? H2 minus, it has a negative charge. That means it has an extra electron. So the way you would do that is you would start by, again, with the atoms on the sides. But now this time, one of your atoms has an extra electron. So give one of the hydrogens an extra electron. So that means that one of these is going to be negative. So why don't we just make this one negative, right? So we have H minus, and this one has an extra electron. So now that has this has 2 electrons. This is just hydrogen with 1 electron. So when you add these together, then the molecule will have an extra electron as well. So how do you do this? So now we have 3 electrons here. And so we're going to have 3 electrons building up from bottom to top. So here we have our 2 electrons here. We have 1 other electron, so that other electron is going to go up to the next higher molecular orbital. So that electron is going to be spin up there. So then here's our molecular orbital diagram for H2 minus. And so how would you do the bond order of that? Same way. So the bond order for H2 minus is going to be, again, bond order is equal to, this time we have 2 bonding electrons, and then we have 1 non-bonding electron. So we're going to subtract 1, and then we're going to divide by 2, so we get 1/2. So we got a half a bond order. Means we got pretty much a half a bond. So for that, you might draw it like this. So a little dashed line instead of a solid line. So that we have a fractional bond here instead of a full bond. So 1/2 of a bond. Okay. And so the next one is, what if we have a H plus? We have H2 plus. So that means that we have 1 less electron than we should have, right? So that means that one of our atoms is missing an electron. So if we make this one a plus, that's going to make our molecule a plus. So we're missing an electron. So that means that H plus has no electrons. So there's no electrons for this hydrogen atom. And this hydrogen atom has 1 electron. So that means that when we fill in our molecular orbital diagram, then this electron comes down here. So we're only going to have 1 electron, right? So this electron is the only one there. So this is our orbital diagram for H2 plus. And so now we can do the bond order for H2 plus. So if we do H2 plus, so the bond order is equal to, now the number of bonding electrons is 1. Non-bonding electrons or anti-bonding electrons is 0. Divided by 2. And again, the bond order is equal to 1/2. So we got 1/2 here, we've got 1 here, and we got 1/2 here. So the negative and positive have 1/2 a bond order, meaning half a bond. And so given the bond order, we would then be able to determine that H2 is going to be more stable, the bond is going to be stronger, the bond is going to be shorter compared to either of these. So either of these only have 1/2 a bond, or a bond order of 1/2, meaning that it's not as strong of a bond. The bond strength is lower, the length of the bond is going to be longer, and it's going to be less stable. So these are going to be weaker bonds than this one. And so that's how you can use molecular orbital theory to determine the stability of different molecules based on bond order. Okay, well, I hope this was helpful. I hope you found this clear. And if you have any questions, please feel free to make a comment in the comment section. If you like this video, share this video, hit the like button, hit the notification bell for more videos, and hit the subscription button to subscribe to the channel. Again, make a comment in the comment section. Let me know what you think, and if you have any questions you want me to answer. Thanks for joining me, and I'll see you next time.